Welcome to this explainer. Today, we are building something genuinely incredible, a conceptual map of gravitation. We aren't just memorizing isolated formulas here. We're going to visually connect the dots, step by step, from the foundational rules of attraction all the way to the mind-bending experience of weightlessness in space. We'll be walking through all the steps of these physical derivations to give you the deepest possible understanding of how the cosmos actually ticks. Here is our roadmap for today. We're going to hit the universal gravity rule, Kepler's orbital geometry, derive areal velocity, map out potential energy, look at some field analogies, and wrap up with the weightlessness phenomenon. Let's just jump right in. Section 1. The universal gravity rule. So let's start with our very first node, Newton's universal law. Look at that equation. F equals big G times big M times little m, all divided by r squared. Basically, this invisible force of attraction is perfectly locked in by the two masses involved and the distance between them. The larger the masses, the stronger the pull. But look closely at that denominator, the distance squared. That is where the magic really happens. And this perfectly illustrates the inverse square law in action. Think about two rockets moving apart. Because that distance, r, is squared in the denominator, simply doubling your distance from a planet doesn't just, cut the gravity in half. No way, it slashes it to a mere quarter. It's a massive drop-off, showing exactly why gravity loses its grip so fast the further out into space we travel. Moving on to Section 2, Kepler's orbital geometry. Now, for centuries, people believed orbits were perfect circles, but actually planets move in squashed circles, mathematically known as ellipses. Imagine drawing a circle but physically stretching it out from two sides. That's what the cosmos naturally prefers. And the crucial takeaway for our conceptual map here is that the sun isn't sitting right in the center. It's off to the side at a specific coordinate called a focus. Because of this stretched out geometry, a planet's distance from the sun is always changing. This gives us a mathematical closest point, the perihelion, which is just calculated by a times 1 minus e, and a farthest point, the aphelion, calculated by a times 1 plus e. That e stands for eccentricity. Basically, it just measures exactly how squashed our orbital map really is. All right, Section 3, deriving areal velocity. Before we get into the heavy math, we have to ask a physical question, one that Kepler actually noticed but couldn't immediately explain with physics. If a planet's distance from the sun is constantly changing, why exactly does it hit the gas pedal as it gets closer and then slam on the brakes as it moves further away? Let's step through this derivation map to really understand it. Step 1. Gravity is a central pulling force, meaning the net torque on the planet is exactly 0. Step 2, because torque is 0, the planet's angular momentum is completely locked in. It can't change. Then, steps 3 and 4 show how this constant momentum mathematically forces the planet to sweep out equal areas in equal amounts of time. To keep that areal velocity constant, the planet literally has to travel faster when its radius shrinks. It's exactly like an ice skater pulling their arms in to spin way faster. This is where it all really comes together. By setting the angular momentum at the aphelion equal to the perihelion and conserving total energy, we can calculate the exact blazing speeds at a planet's closest and farthest points. It is just perfect, predictable clockwork. We wrap up this geometric node with Kepler's third law, which elegantly proves that the time it takes a planet to orbit is directly tied to the sheer size of its ellipse. You square the time period, you cube the semi-major axis, and boom, you have a cosmic ratio that holds true for every single planet in our solar system. This is the literal math scientists use to predict exactly where a planet will be years from now and how we navigate probes to the deep outer edges of the solar system. Section 4. Mapping potential energy. Instead of just blindly memorizing a final formula, let's actually trace the work done step by step on our derivation map. In steps 1 and 2, we take a tiny microscopic distance step, delta r, and multiply it by our gravity force. Then, step 3, we integrate. We sum up all those tiny amounts of work required to push a mass all the way out to infinity. Finally, step 4 brings us to our total potential energy formula, U equals negative gmm over r. Section 5. Field analogies and variations. Notice how beautifully physics repeats itself here. The math of gravitational fields perfectly mirrors electrostatic fields. Where electrostatics uses the constant k and charges q, gravitation just swaps in the constant g and mass is m. The main difference? That attractive minus sign acting as our cosmic glue. Honestly, if you know one formula, you conceptually know the other. The big takeaway from these variations is that Earth's gravity isn't just a static 9.8 meters per second squared everywhere you go. It dynamically weakens. Whether you dig a deep tunnel way down into the Earth at depth D or fly high above it at height h, the gravitational field drops off based on these specific proportional multipliers. It's constantly shifting. And finally, Section 6, the weightlessness phenomenon. It sounds like a total paradox when you first think about it. If gravity is constantly pulling us toward the center of the Earth, how can a space station be continuously falling but never actually hit the ground? The secret here is pure geometry, extreme horizontal speed perfectly matched with the Earth's curve. The Earth's spherical surface curves downward by roughly 5 meters for every 8 kilometers you travel horizontally. So if you can shoot a satellite horizontally so incredibly fast that it travels 8 kilometers in the exact same time it takes to drop 5 meters, the satellite falls at the exact same rate that the curved Earth drops away beneath it. This isn't just a fun theory. This exact principle is what keeps our GPS and communication satellites perfectly in orbit so our phones work every single day. And this gives us true weightlessness. Because the astronaut, the spaceship, and, say, an apple floating inside the cabin are all traveling at that exact same extreme horizontal speed, they are all in an identical state of free fall. With no floor pushing back up against them, they experience the absolute astonishment of complete zero gravity. So the astronauts aren't truly escaping gravity. They're just falling so incredibly fast that they keep missing the ground. We've mapped out the mathematical nodes today, from Newton's inverse square law, through all the steps of Kepler's geometries, right up to orbital weightlessness. To wrap up this explainer, I want to leave you with a final provocative thought. If the invisible strings of gravity stretch mathematically to infinity, mapping the orbit of every single moon, planet, and star, are we all just engaged in one giant, perfectly mapped cosmic freefall? Thanks for exploring this conceptual map with me today, and keep learning.